The big and small problem number 2 involves our bowling ball and golf ball that are both undergoing pure translational motion, and they begin their motion with the same initial non-zero linear momentum. What we're going to do is apply the same constant net force to each ball as they undergo their motions, and that force is going to be in the opposite direction of each ball's motion, and we're going to try to determine which ball takes more time to stop under the influence of that same net force. So will the bowling ball take more time to stop than the golf ball, or they both possibly take the same time, or there'll be not enough information to tell? And when I start thinking about the idea of calculating a time, in this case a time to stop, I might have the urge to go back to the very first part of the course and use some of the kinematic relationships that relate position, velocity, and acceleration to time. But as we've moved through the course and developed a few more advanced techniques, I might think about applying some of the ideas that I learned in block number 5 with work and energy, or now in block 6, impulse and momentum. So if I look at the problem statement, one of the things that I'll notice is that both balls start off with the same initial non-zero linear momentum P. The initial momentum vector for the bowling ball is equal to the initial linear momentum vector of the golf ball. And that might be something that we can use as we further analyze the problem. Something else we're told is that both balls are going to be affected by the same constant net force. So if I call that force F and then use the subscripts net, cis, and av to represent the net average force that acts on my system, then that same net force is going to act on both balls. And when I talk about my system, when I'm looking at the motion of the bowling ball, the system is going to be the bowling ball B. When I'm looking at the motion of the golf ball, my system is going to be the golf ball represented by the subscript G. Under the influence of that force, both balls eventually come to a stop. And so the final velocity of each ball is going to be 0. And likewise, the final linear momentum vector for each ball is also going to be 0. So the final linear momentum of the bowling ball and the final linear momentum of the golf ball are both going to be equal to the 0 vector. Both balls come to a stop. Now, this may not seem like it's a lot of useful information when we first start tackling this problem, but we have a very, very powerful idea that we're introducing in this topic, and that's the one of the change in the linear momentum that a system can undergo as its initial linear momentum increases or decreases or changes to some final value at some later time during the motion of the object. So the change in the linear momentum of our system is just the final linear momentum value of the system minus the initial linear momentum value of the system. And remember, these changes are always final values minus initial values. For both the bowling ball and the golf ball, we're going to find out that both have the exact same change in their linear momentum values. Why is that? Well, look at the final linear momentum of both the bowling ball and the golf ball. Since both balls come to a stop, those final values are both 0. The initial linear momentum of the bowling ball and the golf ball are equal to each other. We were told that as one of the conditions in this problem. So it turns out, since both balls start with the same 0 amount of, well, they both have the same final linear momentum of 0, and they both have the same initial linear momentum that's equal to each other, the total change in the linear momentum of both systems is going to be the same. So both the bowling ball and the golf ball experience the same change in linear momentum. The impulse momentum theorem tells us that that change in linear momentum is related to the net impulse that that particular system or object experiences. So the change in the linear momentum of the bowling ball is related to the net impulse on the bowling ball, and likewise, the change in the linear momentum of the golf ball is related to the net impulse on the golf ball. So those expressions there are what we call the impulse momentum theorem, the idea that the change in the momentum of the system is related to the net impulse on the system. From our first slide, we were introduced to an equation in the box that said that either the change in the linear momentum of our system or the impulse that acts on our system is related to the net average force on the system times the time over which that force acts. And so for the bowling ball, the net average force that acts on the bowling ball times the amount of time that force acts on the bowling ball is going to be related to both the net impulse and the change in momentum of the bowling ball. And likewise for the golf ball, there's going to be some sort of net average force on the golf ball and some sort of time during which that force acts is going to cause this net impulse and change in momentum of the golf ball. Since we're told that both balls experience the same net average force, we know that those two forces are equal, and in order for this equation to be true, those two time intervals, delta t for the bowling ball, and delta t for the golf ball are going to have to be the same. And those time intervals are basically the stopping times, the time that those forces act on each ball. So that tells us that both balls are going to have the same stopping time, and it's going to take the exact same amount of time for both balls to come to a stop. That might be counterintuitive to your thinking, because if you think of a big, heavy, massive bowling ball rolling compared to a small, lightweight golf ball, you might think it's got to be a little bit more difficult to stop the bowling ball than the golf ball. But if you're told that they both have the exact same initial linear momentum and they're both stopped by the same constant net force, what our analysis shows is that they both take the exact same amount of time to come to a stop. So under those conditions, we get answer C. Another problem that we can look at with the bowling ball and the golf ball is going to be embodied in this problem called big and small number 3. And again, both balls are undergoing pure translational motion. They start with the same initial non-zero linear momentum. And we're going to apply, once again, the same constant net force to both balls that oppose the motion of the balls. And as those forces act on the balls and cause the balls to stop, what we're going to ask in this question is, which ball travels further before coming to a stop? Will it be the bowling ball, the golf ball, or they travel the same distance, or do not have enough information to tell? And this problem is very, very similar to the big and small problem number 2, but in this earlier problem, we were asking which ball took the longer amount of time to come to a stop. And we found under these same conditions that both balls required the same amount of time. So think about this. We'll come back in the next video with the answer and see what we get.